Okay, so this is the first set of video examples in chapter 17. So this time we're looking at some potential energy or voltage problems in electricity. So let's see what we have first. So first our problem says, well, we want to look at the potential due to a single point charge. So first it says determine the potential at a point that's 0.5 meters from a charge that's 20 microcoulombs. And then the same thing, except what if the charge is negative? So I highly recommend that you make sure you watch that Kahn video on that derives this point charge voltage equation. Even if you haven't had calculus, I think it might be a little bit informative. And if you have had calculus, the calculus part of it's pretty darn simple. So definitely worth watching. Anyway, so this is the voltage of a single point charge, so we use that formula and we plug in 0.5 for the radius down here, and we plug in 20 microcoulombs, so 20 times 10 to the negative 6 for the charge, and K is just the Coulomb constant. And look at they've got all their units here. I guess we could do a little dimensional analysis. So if K is meters squared for Coulomb squared times newtons, and we've got this is going to cancel with this, right? And then it looks like one of the meters is going to cancel with this meters. So if we look at our units, we have Newton meters per Coulomb. So that is volts, if you remember. Anyway, so if we multiply those numbers, we get a voltage of this guy due to that single point charge at a radius of 0.5 meters away. So notice this is just thinking about we've got a single positive 20 Coulomb charge and we're looking some radius away at like where this is 0.5 meters from there to there, except it's not bent. So for the negative charge, I think that, remember, when you're doing voltages, you do have to take into account positive and negative. Remember, voltage is a scalar quantity, so it doesn't really have direction, but it does have a positive or negative part, so that's all you have to worry about. Anyway, so same thing, except now this is negative, so it's going to be that same voltage, except now it's going to be negative. Okay, so like I like their little note down here. It says potential can be positive or negative. That's in contrast to like how strong an electric field was when we just ignored the sign. Okay. All right. Let's look at another problem. So this one says what minimum work must be done by a force to bring a charge that's 3 microcoulombs, basically from like infinity. So we're bringing it from a very far distance away, and we want to bring it really close, 0.5 meters away. Well, I guess that's like 1.5 feet away from this bigger charge that's also positive. So let's just picture that. So we've got a 20 microcoulomb charge right here that's positive, and we're trying to come in at it with this smaller 3 positive charge, and we want to bring it in so that when we're finally done, these guys kind of balance out, I guess, at a radius of 0.5 meters from here to here. So obviously, since they're both positive, it takes work to push this guy down in that close because they're trying to repel each other. So I don't really like the book's notation here, so I'm going to point out a couple things. So work, remember we're trying to say what minimum work. So I guess if we're problem solving, we're saying work is what? Right? So work, remember, is like just, you can think of it one way as the change in potential energy. So, and potential energy is in this chapter we learned that potential energy is just like charge times some change in voltage, and they go V sub B minus V sub A. I don't like that. I want to go back to our notation from before and call this V final and V initial. Okay, so since these are both like point charges, we're going to have 2 point charge applications of that formula for the voltage. So this is also going to be radius final and radius initial. Okay, so the work is going to be that change in voltage pretty much where you have the charge out here. So what charge is what, right? We have 2 charges in this situation. So this charge out here is going to be the charge that we have for that entire trip, right? So that's the charge that's not changing at all. So over that entire trip, the charge that's not changing is our 3 microcoulombs. So you can see that they have Q plugged in down here as our 3 microcoulombs. Okay? The inside charge is going to be the charge that we're comparing it to, right? So I like what they say up here when they say to find the work we cannot simply multiply the force times the distance. Work is force times distance, right, in general. Work is just, so in this case it'd be like electric force times distance, right? And the reason for that is because the force is not constant, right? Like when you're very far away, this guy's not exerting much force out that way because of its electric field lines that are going like this or something, right? We've seen what electric field lines look like. But as you get closer and closer, that force changes. So since force isn't constant, you can't just use this equation. This guy is not applicable. What is true, though, is that we can just do the voltage at those 2 points that we're considering. So I think we're considering like from really, really far away. They said take R equal infinity. So that's like the initial R. So this guy is infinity down here. And the final R is what they said they wanted to make this one 0.5. That's what they said, bring it that close, right? So remember, if you divide by infinity, that's whatever number it is divided by something infinitely large, so this guy is going to go to 0. So all we really have left is this part over here. So that's what they do. They have that left over here. So at the final distance, the charge that's exerting that force is going to be this charge of 20 microcoulombs, so 20 or 2 times 10 to the 5th, whatever. And then you just plug in your K, you plug in your radius, and there you go. So that's kind of how they did that one. Alrighty, let's look at another one. I like the book's comment in terms of this is like the same problem we did in chapter 16. I think that this time, though, we're not trying to find the electric field or the force just due to Coulomb's law, but we have the same geometry set up, and we're trying to say first, what's the electrical potential or the voltage here, and then we'll do it at point B. So if we're at point A and we've got a positive charge of 50 microcoulombs down here, I guess we'll go and make it red like they do, and then we have a negative charge of the same magnitude a little bit farther away. Remember, voltage is a scalar quantity, so it's not too hard to figure out what the voltages are. You just add them up. So you just do 2 point charge things. So I'm going to factor out the K, if that's all right with you guys. Oh my gosh, that's kind of ugly, but it'll do. So the voltage is just going to be the potential due to this guy and the potential due to this guy. So I think that's all we basically need to do. So this guy was, we'll do KQ over R. So K and Q is 50 microcoulombs over R. Let's see, that's 30 centimeters, so 0.3. Remember, this is not like Coulomb's law where it's an inverse squared law. It's just an inverse law, no squared right there. Okay, and then this guy is negative, so I think his influence is going to be negative 50 microcoulombs, and this would just cancel out, but he's not the same distance away. Looks like the geometry says he's 60 centimeters away, so that's what's going to happen there. So since we're dividing by a bigger number here, I think we're going to be ultimately subtracting something less. So let's see, so we plug in K, and K is 9 times 10 to the 9th, if you remember, so do those computations, and I think you get 1.5 million volts for this guy, in other words, due to the positive charge, and not quite as much is subtracted by that negative charge, about 7,500,000 volts when you plug that guy into your calculator. So you get, let's see, 7.5 times 10 to the 5th volts. So if we're up here in this guy's spot, we have that much positive potential energy. And I think that that makes sense because this guy is contributing more potential energy than this guy because he's closer. So kind of like being, um, well, I don't want to take it farther than that. Anyway, so what about at point B? So let me erase all this stuff. Give me just a sec. Okay, so we'll start over, and now we'll go at point B. And I think you'll probably have some problems like this where you have to do a little bit of geometry. Oh my goodness. Hopefully that isn't a big deal. So anyway, this time looks like we're the same distance from each, so I think you could probably guess that the voltage due to the symmetry of this situation is going to be, you guessed it, 0. But all you'd have to do is add it up. If you have a problem where you have to use a little geometry, use a little geometry. So we could use some geometry to make sure that's the case, right? So since these are positive and negative, we're going to have a 0 voltage on this one, but I guess we'd have to figure this out technically. So since that's 30 and that's 26, oh yeah, we don't even have to do Pythagoras, do we? Can't we just use geometry and say side, angle, side, side, angle, side, SAS? These triangles are congruent by SAS, so we already know that this has got to be 40 centimeters. So since the charges are equal magnitude, opposite sign, there's going to be 0 voltage at point B. No potential energy. And that would make sense if we did it with an electric field too, like from last chapter, because the electric field would basically be 0 right there. They'd be canceling each other out. The vectors would try to like cross each other out, and we wouldn't have any net effect. So let's look at one last situation this video. So this time we've got a couple different situations. We got, let's imagine all these charges have the same charge, so maybe we should just go 5 microcoulombs for each one. Okay, so same magnitude for all these situations. The first question is, what set has a positive potential energy? So which one has the most potential energy, in other words, so that it's positive? If you just think about it, and when I think about potential energy, I go back to the top of a cliff. I use that analogy primarily, but I'm just thinking like what has the most potential to do the most work. It says in the book that potential energy equals the work required to bring two charges near each other if they're starting at a great distance. So if you think about it, I think it's going to require the most work to bring the pluses, to bring these guys together. These guys are going to want to go together right away, aren't they? And these guys are definitely going to also want to go together. The pluses are going to try to repel each other, so if you try to bring them closer, you push each one closer and try to get them really close into this situation that they're in, you're building up more and more energy the closer you push them together. So in other words, you're building up more and more voltage or potential, electric potential, as you bring them closer together. So I think for my first question, A, the two positive charges has the most potential, and it's positive. That's most. So the most potential definitely down there. B says which has the most negative potential energy. Another way to think about that is basically which has the least potential energy. And I think if you consider it, well, it's definitely not number 3 now. So if you think about these two, which will have the least potential energy? And I think the answer is 1, because they're already closer together. Hence, it's going to take even less work to bring them near each other. It's going to take almost nothing. So, I mean, they're going to want to suck together right there and get together as quickly as possible. These guys are also going to want to get together as soon as they can, but they're starting from a little bit farther away, so they're going to have a little bit more potential energy. Once these guys are this close, there's not a whole bunch more that they can do. In other words, they're going to zoom together really fast. So I think that 1 has the least, and it's negative in fact. The least voltage or the least potential. Okay, I think we've had enough of my terrible writing. Okay, hope you found this useful. Bye.